All right, so the recording just started here. Apologies for those that are coming out asynchronously. Haven't really talked a whole lot. Just talked a couple bit about my motivations. You can check out the syllabus to kind of take a look at this online. And I was just finishing up saying that you can, if you'd like to, if you do happen to miss a lecture or you just don't plan on, it isn't convenient for you to come to that lecture, then you can feel free to make use of the recorded lectures, which are online. You can also find the recorded lectures from 2 years ago, the last time I taught that, if that's helpful. And you just do whatever makes the most sense for you. Don't have to clear it with me first. It's totally kind of what we're calling a high flex. It's a flexible hybrid setup here. So, so that's kind of how things are set up. So what else is required? So for reading materials, I've put a couple of texts here that are, I think, pretty nice texts, and they survey a lot of the things that we talk about. And some of the authors here I like, but I'm not requiring you to get any texts. I've put all of the reading materials that you'll need on Canvas. There's also a link to a Dropbox folder and a link to a Google Drive folder where they're all in there already for you. If you don't like the Canvas interface, I'll show you the Canvas interface here in a second. So all of that's already provided for you. So feel free to make use of that. Like I said, for course software, it's really up to you. It's whatever you're comfortable in. So again, about flexibility here. We are kind of sophisticated enough that should be able to grade your assignments when you turn them in. And really your focus will not only be on writing some code, but also presenting a 1 to 2 page outline of what the heck's going on. So so with that in mind there, again, I'm not requiring you to, we're not going to use a particular Python package, for example, or anything like that. A lot of this is we're building from the ground up. And so a number of different packages will work fine for that. So, so that's kind of, before I get into the structure of, what are the assignments for the course? Are there any questions about the requirements, about attendance? Yeah.
For the assignments, so like when we turn them in, since you don't care what we use to code it, are you really just looking for like an explanation of our process and any relevant graphs or stuff for the optimization problem that we were doing?
Yeah, so the question there for those who didn't hear it is that what might we be looking for the assignments? And I will talk about that on the next page here. So so that's something that'll come up, but I'll get exactly to that. So any other questions? Yeah.
Hello, Professor. Hello.
Yeah, pardon. There's somebody kind of online. I'll get to the online question in just a second.
Yeah,
I'm
sure.
just handling an in-person question here, and then you'll be the next one. Yeah, sorry. So you said about the PhD approved elective. You were eligible, absolutely. So I say approved elective here. So what I mean by that, it's an approved CS elective, and so it's not like an outside elective. And so that's just meant that if you're in the CS, if you're going through the handbook for CS, if you're just choosing on your electives, then this can count as a CS elective. But so you can, I'd say questions about your particular degree programs, I would send to, you can ask advising to clarify, but this, should, for any CS master student, should count as one of your major electives. I'll get to that in the next page. The grading, was that the question was about the grading, right? Yeah, okay, yeah, that'll be on the next page. And then online, there was a question. Could you go ahead and repeat?
Yeah, sure, Professor. So I just wanted to know, can we use this subject as our portfolio? I did see that there's a project being done in this course and I wanted to use it for my portfolio. So just wanted to know if that's acceptable.
Yeah, there's a question online about whether this course could be used for your portfolio. And I'm actually about to get that out on the next page as well.
Okay.
So I'll cover that in just a second. Any other basic questions? Just basic clarifications about anything I've talked about so far, about required materials or attendance stuff. So by attendance, I'm not requiring attendance by any means, but I guess what I'm saying is, like I was saying, that if you would like to attend, regardless of what modality, you'd like to attend in, you can feel free to choose that on your own, you know, in the morning at 10 a.m., decide how you attend. Yeah. Yes, sure, you absolutely could. Any language, even if I didn't list it here, as long as you can implement the desired algorithm and demonstrate whatever is asked of you in that assignment, it doesn't matter to me what platform you use. So we all have diverse backgrounds here. And so, you know, I expect to see a diverse number of submissions. All right, so let me get, so there's a lot of questions. Let me make sure there's nothing special in the chat here. And then I can get to some of those other questions. So there's a question, is C++ and OpenGL permitted for mini projects? So I'll get to whatever mini project is here in a second. So again, I would say that absolutely, if you want to do a project that that makes use of particular platforms, so of course, you know, even if I haven't mentioned C++, C++ would definitely be a fine language to write your assignments in. And about particular library support, depending on the project you're doing, then you might find that at least for your project at the end of the semester, things get much more complicated. And I do think things like OpenGL would be great to incorporate in. But for the mini projects, they'll often be demonstrating something more fundamental, where I'll be asking you to implement something a little bit more from scratch. And so some of the library stuff, if some of the supporting API and libraries that you can find are not related fundamentally to the thing you're trying to implement. So if you're trying to do a multi-objective genetic algorithm, for example, well, in that particular case, you just happen to want to do something that involves computer vision for some reason. And so you decide to use OpenCV. Well, that's fine, because OpenCV isn't fundamental to the multi-objective genetic algorithm. So I don't want you to re-implement a bunch of computer vision stuff that you can just get out. I mean, that would be a perfect place for you to make use of that. But I don't want you to go out and find a genetic algorithm library where everybody's already done the work for you, so you just pop in and get a result out of. So I want you to be able to demonstrate the principle, and as long as the framework that you've chosen hasn't short-circuited that, then I'm happy with you using it. So hopefully that makes sense. Very flexible about however you implement these things. The principles, the fundamental principles are going to be the most important thing. So let me make sure there's nothing else here. Okay, great. All right, so I will get to those specific questions about the assignment schedule. I want to give you kind of a layout of where things are going from here. So this course is organized into units. So like this first unit, we're going to be talking a lot about evolutionary algorithms. I'll talk about what that means here, maybe towards the end of this lecture and definitely the beginning of the next one. And so these are things you've probably heard a little bit about, or if not, you know, significant about, because they're very popular. So things like genetic algorithms and so on. And we will talk about the complications of genetic algorithms, like what do we do about this thing called genetic drift? So what we're going to find out is that with genetic algorithms, particularly ones implemented on computers, you have small population sizes, small relative to some factors that we'll talk about, and they can tend to give you suboptimal solutions due to something called genetic drift. And so that's something that, you know, we'll be talking about here. So these are all not things I'm expecting you to already know, just kind of showing that that's going to be a major highlight of this unit. As we move further on, I'm not going to kind of do the whole class here, but to kind of give you a feel for it, we spend a lot of time these first few weeks covering things related to evolutionary and genetic algorithms. And so these are meta heuristics, where we're going to start with single optimization functions and how to optimize them, and then move into things like genetic programming, artificial immune systems, which are related to that, and then bump things out to when we're optimizing for multiple objectives simultaneously. So then we move on to MOGA, multi-objective genetic algorithms. And then what happens when you take a genetic algorithm and you put it across in distributed groups? And so you might put it across multiple computers, multiple processor cores, why that would be a good thing to do, why that would be a bad thing, what are the pitfalls, what are the pros and the cons, and so on. After going through a kind of a large section on the GA, which is these first kind of 4 units, or on evolutionary algorithms more generally, EA, evolutionary algorithms, then we're going to focus a little bit more on pivoting to, for comparison, to simulated annealing, which is a kind of classic meta heuristic that is commonly used as a benchmark for meta heuristics. And it is physics inspired, not biology inspired, but still nature inspired. And so we talk about, where does simulated annealing come from? What is it doing? Why does it work so darn well? And what might be its pros and cons, and so on. Then after that, we kind of can, we're going to switch fundamentally into these different sorts of algorithms that that actually put agency into the individual optimizers that are running around in these kind of simulated ecosystems. So that's where we start talking about things like ant colony optimization, ACO, which you may have heard of before, and particle swarm optimization, PSO, which you may have heard of before. And so we start introducing that, and then that kind of allows us to pivot away from pure optimization and start talking about some other applications. And so things like multi-agent systems and how they are involved in general numerical processing. And so what does learning about agents trying to optimize something collectively tell us about multi-agent systems that do more general numerics inside a computer? And that then, towards the end of the class, we'll then start do kind of a survey of kind of neural inspired architectures for computing. So we'll talk about artificial neural networks. We'll talk about not just your kind of standard ANN, supervised ANN, but we'll kind of join that together with, well, how could we possibly take all the stuff we've learned about evolution and combine it with neural networks to sort of say, what is an evolvable neural network? And how would that work? And how is that any different than what you might get with more traditional things? We'll talk a little bit about spiking neural networks. It's kind of, it's a neuromorphic computing. And then we'll close the course based on kind of time permitted with an introduction to cellular automata, how you can combine cellular automata with evolutionary methods and what are the benefits of that. And then if, again, time permits, then we can flip to stochastic policies with distributed automation. And so, sometimes people ask me about chemical reaction networks, which is something that we use sometimes in my lab for things. And so I'll see if I can trickle in CRNs, maybe up here in Unit 7 as well. But this is kind of where they would sort of live, I think, normally. So if time permitting, we can hopefully get into those chemical reaction networks at kind of the end of the class there. So it's kind of meant to be, again, a survey of these things, and just to give you some sort of exposure to some of the kind of basic principles in nature-inspired computing. And then through your final project, which I'll be about to talk about here, you'll be able to explore additional angles that maybe we don't cover formally in class, but we hopefully give you some tools that you'll be able to then examine and then display in that final project. So let me flip to that. Let me make sure there's no questions online. And I'm also, while I'm over here, seeing if I can get rid of this thing. Well, that's better, I guess. All right, so any questions online? I don't see any in the chat. All right, so course structure. So the way the points are distributed throughout the course is, so every week I ask you to do one of these things called a muddiest point reflection, which is something which comes up in the pedagogical literature. It's had pretty good results on improving retention. So basically every week, and the lowest 2 of these are dropped, and so you can skip 2 weeks. Every week, there is a very short Canvas survey that each one of you will have the opportunity to fill out, that will be graded for completion, coherence, not correctness, where you basically tell me 3 things. You tell me what was, and you can do this in a sentence each. What is the clearest thing that you learned all week? So the thing that made the most sense to you. What is the muddiest thing from all week? Now, you might think everything's clear, and that's totally fine, but if you were to rank them, what would be at the bottom of the list? What would be the one that's not quite transparent, has just a hinge of opacity, that would be your muddiest point. I just like you to rank those in your head and tell me what's at the top of that list, what's at the bottom of the list. And then the third thing is if there's anything in particular that you'd like to learn more about in future weeks, what would that be? And the answer to that can totally be n/a. It can just be, no, everything's fine. I'm good just rolling with the current schedule. There's nothing else I want to look further into. You don't have to give me much more than that. Again, just a sentence for the first two and then even NA for the last one. I review those just to see if I can do any just-in-time updates. And those little surveys, and if you complete them, you get the full credit for them. That's 5% of your grade. Now we do have these kind of more homeworky things, these what I call concept checks, where the lowest one is dropped. And so about one every unit, there will be an online, it's kind of a quiz format, but it's not timed or anything. You don't have to take it with Respondus or anything like that, where it's just going to ask you about some of the things that we talked about in class, or it might ask you to do a reading related to the stuff we talk about in class and ask you about that reading. And so then you'll do that concept check just to make sure that everybody's kind of on board, like, oh, what is genetic drift? What's a good definition of genetic drift, et cetera, et cetera. And then, so before I had a midterm in here, I got rid of that because one of the feedbacks I got from previous students who took this course, they wanted to do more programming. And so what I decided to do was replace what would be a midterm with per unit, giving you an opportunity to do a little bit of programming, but I don't want you to this to be a major burden on you. And so there are, like I said, about 10 units. We might get through 8 or 9 of them, depending on how quickly we move. And for each unit, if we don't get to a unit, it drops off, so we don't have to worry about that. But for each unit we cover, there will be one of these things I call a unit mini project, which basically is going to be an opportunity for you to demonstrate some principle that was related to an algorithm that we've covered in that unit. And so this might be, you write a little bit of code, you have it produced. So there was a question of, what do these mini projects look like? What are the deliverables we're kind of expecting for this? So you would upload your code, and then you would upload a 1 to 2 page document, which basically, it doesn't have to necessarily be formatted like an extended abstract or anything like that, but it would be something where you sort of say, I was investigating this concept of Pareto optimality or whatever concept you'd like to talk about. I use this particular algorithm. As you can see, when I set things up with these parameters, I get this output figure. When I change it to these parameters, it changes drastically to this. This demonstrates that these parameters are really important for this or something like that. So just something where in 1 to 2 pages, you've shown me that you've implemented an algorithm and you've experimented with an aspect of it, and you're able to demonstrate some fundamental property of that algorithm or extension of that algorithm, and you'll upload those. Now, like I said, I dropped 5 of these things, and again, there's probably only 10 of them max. So the intent for this is not for you to spend all semester working on my class. The idea is you get 3 or 4 times, you stop during the semester, and you say, Ted said something really interesting last week. Hopefully there's more than 1 week I say something interesting, and I'd like to investigate that, and I'm going to upload these. And so there's 60 some of you in this class, and so we might get, for each one of these mini projects, there might only be 15 submissions or something, and that's totally fine. So just as long as you do 3 or 4 of them, because again, there's such a heavy drop policy here, then you'll be able to get credit for these things. So that's kind of meant to be kind of practice along the way. And then at the end of the class, there's going to be an open book final exam during finals week that will be, in order to facilitate all our remote students, it will be administered online, but I'm not going to use Respondus or anything, but it will be a timed thing. So basically, I think because this is a Tuesday class at 10:30, I think our final exam day is also on Tuesday. So what I'm going to do is I'm basically going to open up the final exam availability window from Monday through Wednesday of finals week. And anytime during that window, you can start the exam, and you'll have, 110, maybe I'll add 15 minutes, like 125 minutes to complete the exam. You got to complete it in one shot, but during that 25 minutes, it'll be open book, open Canvas, open notes, but individual. And so at home, kind of trusting you to do to work on that exam on your own and submit it whenever you would like during that Monday to Wednesday period during finals week. And then the last kind of big chunk of your grade, and this answers some of the portfolio questions too, is a final project. Now, I like to do these in groups, preferably groups of 2. So maybe I'll write this here. Is this, I like to do this in groups of 2. There can be exceptions to that rule, but generally I like to have 2 students because it usually kind of, they kind of push each other. Once I get more than that, you get a little bit of freeloading going on, but I don't see that a lot of times in 2. You know, about mid-semester, you're gonna tell me who is in your team. And then you're gonna tell me very briefly what algorithm you would like to study. Now, if you go on to Canvas, and I'll show you Canvas in a second, under the final project module, there are a list of candidate algorithms, and you can come up with additional ones as well, but I put a pretty big list of ones that I think are really cool, but I don't have time to cover myself, that you have an opportunity to check out. There might be extensions of things we talked about in class, or they might be a totally different thing that we just didn't have time to cover in class. And then you and your partner will end up investigating that. So in this algorithm choice, it's a very short assignment. And then, you know, I don't know, like a week or a week and a half later, then you actually tell me what you're going to do to demonstrate some cool principle with that. So you're going to say, I'm going to use the neuroevolution of augmenting trees to implement a neural network that drives a simulated robot around a maze or something like that. And we have this existing platform, simulation platform that we've built in Weebots, where a robot's got a maze. And so we're gonna already have that available to us. And so then we are going to involve the control system using a basic neural network that is designed by the NEAT algorithm or something, you know, et cetera, et cetera. So you can kind of tell me that basically what you're planning on doing, you don't know what the results are yet, but you at least have a game plan. And that's what this proposal is. And I'll check off on those, make sure everybody's heading in the right direction. Likewise, for this algorithm choice, I basically want you to submit that so that I make sure that there's a diversity of algorithms represented across the class. And then the big deliverables for that is during the, the last week of class, during that Wednesday night, you upload, so I'll say Wednesday night by 11:59 p.m., let's say, you upload a 12-minute presentation, as well as a, I think this is, I'd have to check below, but I think I have a 4-page extended abstract. And that goes up onto Canvas. And the reason we do it Wednesday night is that then each one of you will get randomly assigned a report as well as a presentation from another group. And then by Saturday of that so just before finals week, then you will watch the 12-minute presentation you were assigned, and you will read the 4-minute extended abstract, and you'll fill out a rubric that I give you on Canvas, and you'll write some constructive comments, and I'll go through and I'll look at your constructive comments in your rubric, and then I'll give you points on both of these things just for being, you know, just for giving an honest review. And then I'll go through and I will go through and grade each one of the presentations and the reports, and I will make use of not only my evaluation, but the evaluation of the random students that have also applied that. So when you do your peer evaluations, it will be anonymous to those receiving the evaluation, although you'll probably be able to figure out who you're evaluating, but you won't, who is evaluating you will be the anonymous thing, but I'll see that, and I'll be able to use those scores as well as my own scores to come up with a good score for the presentation and the report. Now, I usually lean towards grading a little easier on the final project because this is meant to kind of be a celebration of the work that you've done. And so really the kind of summative stuff comes out of things like the final exam, the unit concept checks. And so I don't want you to stress about the final project, but I want you to do something you're proud of and that you'd be willing for 2 random students to be able to check out, because that's what's going to end up happening here. So that's the way it's kind of lined up here. So that's the base. And because this final project is 40%, I believe the portfolio target is 30%. And so I have had plenty of students use these in their portfolios for RAS, for CS, etc. So if you would like to use these in this project in your portfolio, I'm happy to sign off on that. Question?
Final exam pre-response, or is it more like
Oh yeah, well yeah. So this will be mostly, if not completely, auto-graded. And so it's possible I could put a couple of ones in there, but I'm probably, but then me go through and manually grade them. But at least last semester, I did it all auto-graded. And so it still looked like it was a challenging exam, but it'll be an exam that it's designed for everyone to finish with plenty of time left over, and for me to be able to get scores to you pretty quickly after that. Oh, thank you. Question on Zoom: will mini project algorithms be tested against test cases on Gradescope? So yeah, so there was a question online about, you're going to submit these mini project assignments. Am I going to use Gradescope to do unit testing so that to test them against cases? And that's and no. So that's not the type of thing that I want you to demonstrate. I really want. It's not like, it'd be one thing if I said, build an algorithm to implement exactly this. It's going to have these inputs, it should have these outputs, and I could run through these 15 unit tests and it should pass all 15 of those. That's not what I want you to do here. I want you to sort of take a more scientific perspective, where I want you to say, all right, I'm studying, again, just because genetic drift will be something that comes up pretty soon. I'm studying the effect of population size in genetic algorithms. And I want to show that if I run a genetic algorithm for a particular optimization problem with a small population size, as I increase the population size, then I find that I get a certain result, like maybe I get a better and better result, and maybe talk about a potential speed accuracy trade-off, and so on and so forth. So I want you to do more of, this is less about building exactly the algorithm to do exactly the particular spec. It is more about understanding the fundamentals of how that algorithm works. So when you as a programmer are stuck with the degrees of freedom of, how do I choose these parameters? How do I choose my population size? How do I choose my mutation rate? And so on, you will have some intuition as to why the mutation rate needs to be small or large, and how that relates to the population size, and how that relates to other things like crossover operators and so on and so forth. So it's really about learning about the algorithms as opposed to implementing the algorithms. So there won't be Gradescope and there won't be unit tests. Yeah. Thank you, very good question. So these presentations will be, so all of these here will be recorded and uploaded. And that's, again, so we do peer reviews. And so you're going to upload a 12-minute presentation. I have guidelines. If you've never recorded a presentation, Zoom makes it very easily to do, but there's other ways to do it as well. I've got some instructions online on Canvas for that. And so you'll upload that presentation, and that allows 2 random peers to be able to watch it in the convenience of their own homes at their own time, so they can do that peer review. Any other questions? I'm going to wander over to the terminal here, but in class, if you also have any other questions. Okay. All right, great. All right, so that's the basic structure of how grades are put together. If you want more details, you can check out the rest of the syllabus, kind of expand, like pretty much everything that I've talked about here, I've written out here in the syllabus in this kind of form. You know, I've got the 12-minute, talk about the video presentation, so it's all there in the syllabus. For the grade ranges here, I use a really simple grading scale, but I always get this question at the end of the semester, will there be pluses or minuses? And I start with this simple grading scale, and then if I see that there are clusters. So there's like definitely a high A group and a low A group, a high B group and a low B group. Then I can add pluses and things to help discriminate among those, so that now if there's a big smooth distribution where there's a bunch of people that got, you know, from 93 to 96, and there's no real bimodality and so on and so forth, I'll probably just stick to this. So nominally, this is what you're guaranteed. If you get a 90%, you're guaranteed an A, but you might get higher than that. So if you get a 90%, you're not going to get an A minus, but if you get an 89%, it's possible you can get a B plus depending on the way the distribution, or an A minus depending on the distribution of how things look. So I use the pluses and minuses to kind of allow me a little bit of flexibility, but there's real simple thing here. So again, I know I'll get this question again, but that's the plus and minus policy there. All right, any other questions about that? Yeah. Right, well, so the key point here, it's kind of a heuristic, is that we drop 5. So your 5 lowest are dropped. And if you think about it, we've got 10 units. And so there is a unit mini project already available for unit 1. And I just need to populate them, but there will be ones for at least these, 8 units total. Now, if it looks like we almost always get to cellular automata, so we'll probably get to unit 9. So the idea here is that for each unit that we cover, you'll have an opportunity to do one of these mini projects. If you happen to not do one, it'll just be recorded as 0, but your lowest 5 are dropped. So the idea here is what I'm trying to do, implementing in the programming language of Canvas, is to sort of say, I want you to do about 3 or 4 of these mini projects. If you want to do all 10, that's fine, and you'll get graded for that. But your lowest 5 will be dropped before we take that grade. So if 5 of them are zeros, they could be 5 hundreds, it could be 5 zeros, Canvas won't know. Does that make sense? Yeah.
We're like, let's say on unit 8, for example, and I decide I want to do the mini project on unit 6. I didn't do that one. Can I go back and do it, or is it already going to be due later?
Excellent question. So ideally, in a perfect world, I would let you turn in these mini projects whenever you wanted them to. But I'm a little worried. This is my first semester doing the mini projects, and I'm a little worried about the grading burden, because the last thing I want is having 60, at the last week of class, everybody decides to turn in 3 mini projects or something like that. And then I've got this, this big burden. So let me think if there's any more flexible way to do that. But for now, the mini projects have a due date. So the mini project for unit 1 is due like January 31st or something like that. It's on Canvas. So I'll try to give you, a week, 2 weeks to do the mini projects. And things might get a little compressed towards the end of the week just because we run out of time. There is a TA for the course. And so that's kind of an interesting thing, by the way, about enrollment. So just kind of, the mechanics of how universities work, there's this magical threshold of 50 students for an in-person class to get a 10-hour TA. And so the interesting thing about this is like, if you happen to get under 50 students, you do all the grading yourself. You get over 50 students, you get someone else to help you with the grading, and one of the grad students in the department gets a job. So a really good strategy, if you kind of think of the game theory of it as a student, is when you find a class you want to take, recruit as many students as you can to take that class. Because what will happen is you'll get a bimodal distribution of, so this is of population, or let's say of enrollment count, across all the courses in a department, where the TA threshold will be here. And so what that means is that all of these courses have a TA that allows you to get your assignments back and graded very quickly. And it also helps ensure that there's a job provided for a grad student out there. So it increases the number of jobs in the department, and it makes the response time much better. And the courses down here are going to be so small that even though there's one faculty member doing it, they'll still be pretty responsive. So this is an ideal distribution. Now, what often happens is people don't kind of recruit students to good classes, and you end up getting something that looks like, well, even looks kind of like, so this is our 50 student threshold, so it looks maybe a little bit like this. And so this is kind of the donut hole of hell, because in this case here, you've got so many students that the faculty member is going to be terrible, at being responsive. Grades are going to take weeks. It's going to be a terrible experience for everyone, and nobody will be enrolled as a TA because the TA threshold wasn't triggered. So, so that's kind of, just kind of for strategizing as you're taking courses at the university. If you find a course that you really want to be a good experience, recruit people to it, so that you can hopefully just create this bimodal distribution. So fortunately enough, we got, I think, 60 some students in this class, which I'm really happy about. So we do get that TA, which allows me to hopefully have a much more responsive class. Whereas I would, maybe cut a lot more things out if I was in the kind of 40-person range. If I was in like the 12-person range, then we'd be all sitting around in a circle, talking papers every week or something. So anyways, it's kind of a tangent, but just kind of a thing to think about. All right, let me make sure that there are no other questions online. All right, good. Yeah. Do we have a what? Yeah, we do have a TA for the class. Yep. And so the TA will be helping me with grading and responding to students. This is a TA who is a student in my laboratory, who's familiar with these algorithms. And so we'll have that additional support as well. All right, so other things I guess I should just mention, if you're interested in late policy, stuff like that, it's pretty standard stuff. Basically, only thing I'll mention about late policy is there's no graded late policy. If something happens that requires you to turn something in late, then generally there's no, it generally has to be something medical, or has to be something that is one of the excused, so there are certain things, there's certain categories of things in the university which allow for missed assignments, allow for late policies and so on, sports, et cetera, but you have to let me know ahead of time. Religious observances, you have to let me know all of those things ahead of time. So if there's anything you anticipate coming up that will cause you to miss some, I don't know, we have a lot, again, flexibility things here, but if you see any deadlines coming up, you see the problems, let me know ahead of time, not afterward. If you do have a medical thing, or you have to be taken out of the class, or you really were planning on getting things in by a certain time, but then you had to go to the hospital or whatever, well, that's of course a little bit different. But once you're well enough to contact me, then that's when you tell me like, oh, I had to go to the hospital or whatever. Don't wait until the end of the semester and say, oh, by the way, I didn't turn in that mini project because in week 4 I was feeling sick and I couldn't do it. So if you were feeling well enough to participate in the class again by week 5, then, or week whatever 6 or 7, then that's when you tell me. So as soon as possible. Grade correction policy. If you do notice, again, just to manage the grading burden, I give you a week. So after I post the grades, you got a week to, if you notice, to find errors. After that week, then again, I'm trying to eliminate 60 students with 3 grades each coming to me at the end of the semester, all needing grade correction. So use the week after grades are posted to look for errors. The only other big things here, don't sell your notes, don't post any solution sets anywhere that I give you, which I hope is pretty standard. If there's any Title IX particular issues, there's there are a whole bunch of resources online. Do know that if anything does come up, of course, I want you to be able to talk to me, but I am a mandated reporter as a faculty member. And so if you report anything to me, it falls under Title IX, I have to report it. But there are counseling centers on campus where they do not have the mandating reporter designation that you can talk to with a little bit more privacy. So So that's something I just want to mention. If you need any accommodations for disabilities, then definitely take a look at our Disability Resource Center, now called SAILS, and I'm happy to work with SAILS. So get flexible deadlines or extra time on assignments or whatever, just work through SAILS and we'll get that made, we'll get that set up. And I think that's basically it for the policies. I do want to, just because there's a lot on there, I do want to share the Canvas webpage just for a second here. So share. All right, so when you come into Canvas, this is kind of the home page, which hopefully you've seen here, about all the really kind of important stuff that you might need immediately, like the link for how to connect to the synchronous, how to connect over Zoom. It's right there. It's right on the home page. That's the URL right there. I know I got that. I'll get that email. The other thing is, if you're looking for recorded things, quick link down here, asynchronous access. It's right there. If you click on that, all of the recordings and the PDFs of the whiteboards that I use will be saved right there. So that's where you find them. It may take me a couple hours to get them online after each class, but that's where they'll go up. So look for them there. Office hours information for now. If you need to meet with me, feel free to make an appointment. All office hours will be over Zoom. And then I'm going to look at my schedule as things kind of shake out this first week, and I'll set some office hours and I'll post them at this office hours link on the front page of Canvas here. Otherwise, most everything in this Canvas, so there is a Slack workspace, feel free to use it. I might add an ed discussion, which is a new tool that they've paid for in Fulton that I'll add in here. That's kind of nice for the discussion board, but of course there's Canvas discussions as well. Feel free to use Slack. I'll post announcements there. I'll also be happy to answer questions there. There's, like I said, also the Dropbox, which you can find here, and the Google Drive. Both those store a lot of resources for the course, like all our PDF readings, audio recordings for the course, etc., will be right there. The big thing I want to highlight, if you go into modules, that's about where everything's organized. You can find things under assignments as well. So I mean, maybe if I click on assignments, a lot of students I notice don't have noticed these boxes up here, show by date, show by type. So you can sort by different things. And so like all the muddiest point reflections, if you show by site, type get grouped together, but otherwise you can find everything by date here. But all of that is also organized under modules. So there's a lot in modules here. So what I would recommend doing whenever you go into modules is just smash this collapse all button and first. And the way I've organized things is that the course information that you probably only need this week is all in this first tab. And so stuff about Canvas, stuff about, getting remote access and so on is all in here. If you aren't familiar, there is a process for accessing journal articles when you're off campus. If in your projects you want to download an article that you don't have access to, but you're at home and you don't have access to that journal, you can take a look at these instructions for accessing journal articles off campus. It'll show you how to get library level access when off campus, which can be really useful. So that's where to find most of the major course information. Classroom recordings, again, you can find them here. I've got the classroom recordings for the previous semesters here as well. There is a blog that mirrors these recordings. So there's a spot off of campus where you can find these recordings as well. Again, the Dropbox folder, there's the YouTube playlist of all the lectures will be there. So all of that stuff is easily available there. Now, at the end of the semester, this final exam folder, well, it's already populated. You can't get into the final exam right now, but there is a practice exam which randomly draws questions from all of the concept checks. And so, so that's kind of an opportunity to practice for this final exam. The final project stuff, we got all stored in here. So this candidate algorithms for detailed study and final project, if I open that up, in another, then this is go through right now. There we go. This is something I'm not going to go through right now, but this is just an example where if you scroll through this, I've basically listed some of my favorite algorithms, like age, fitness, Pareto optimization. That's a popular one that you can read a little blurb about, and you can say, that sounds really cool. I'd like to study that a little bit more. I'll use that for my project. If after reading through all these, you're like, wow, I was really hoping this other one would be on there. I think it's nature inspired. That's fine. Just let me know. Say, Ted, I really wanted to study, I don't know, I'm looking up these, of course, are already on here. I really want to study the Brickyard inspired optimization algorithm or something like that. And if you can just sort of tell me what it is, give me a link to it, why you think it's relevant to the class, then I'm happy with you doing that. But these are just some ideas of where to start. So that's where you find that for the final project. All of the deliverables will also be in that module. So that's where you'll end up submitting all of those. Then the actual units are organized. They're all organized roughly this way, where I'm going to have a set of learning outcomes, and you can view this as kind of a study guide for each of the units. And so each unit has at the top of it the things that I'm hoping that we'll learn from that unit. So you're sort of, when you want to look back for your Muddiest Point reflections or for your unit mini projects, you can look at these learning outcomes and you can say, okay, these are the principles that Ted wanted me to learn this unit. What can I do with them in a mini project? So that's kind of, and so each one of the units has one of these learning outcomes, which you can also think of as kind of a study guide for that unit. Then there's also a section readings. Now, I dump a whole lot of readings that I'm just excited about, but we won't cover, and I'm not expecting you to read. But this is going to be things that when I go through the lecture and I build the lectures on my own, I go out and find these, and these are things that are going to inspire some of the things I talk about, and these are also going to provide extra info for things that you might hear that you want to learn more about. So this is more of a, unless I have a concept check that actually says specifically go and read this one and respond to these questions from it, then these are not meant to be for you to think that I need to read these every week. If you want to read these every week, that's great. I'd be really excited for that and love to chat with you about them, but not required. So you can think of these as sort of after the fact. I want more info. I don't have a textbook. Where do I go? These are kind of take the place of the textbook for additional reference. And then at the bottom of every unit, then that's where you find the assignments. So for unit 1, you can see that I've got the concept check listed there. Concept check 1, so that's going to be kind of an auto-graded concept check of the things we're going to learn in unit 1, which you'll do after unit 1. That right now is set to be due January 21st. And then the mini project 1, where the first mini project, I provide a lot of structure as an example of what a mini project might look like. And so, but in all the other mini projects, it's going to be a little bit more open-ended. So the mini project 1 is not only supposed to be kind of a summative, informative assignment about genetic algorithms, but it will also be a model for the way you can structure your own mini projects in the other units. And for this one, I provided some additional notes to help you with that particular mini project. And that's how all of the units will be structured. I need to go through and populate their mini project assignments and put some rubrics in and so on. But if you were to go through every unit, you'd see roughly the same thing. And that's basically how the Canvas page is laid out. I know it looks like a lot, but I think if you again go up into modules, hit that smash that collapse all, then it's a little easier to navigate. And then I hope the parallelism makes it easy to navigate after that. So any questions about course organization, Canvas organization, where to find things? Also check online. So let me stop this share. And I'm going to go back to this share. All right, no questions online. All right, so in the last couple minutes of the class here, I just want to start, so let me reshare this. And I want to motivate some of the technical ideas. Share screen. So there was a question online that says, let me lock the orientation here. It says, do I recommend any simulators for observing behavior, sort of agents in a world? So we'll talk a bit about, when we get to kind of more agent-based things, we can talk more about that. But there's, I guess, this particular question somebody asked online, are there particular simulators I'd recommend for observing agents? It kind of depends on what you're interested in. You know, there are tools that I can recommend for you if you have videos of human behavior or other animal behavior. How do you annotate those videos and quickly make sense of them? There are also tools for simulating, simple tools like NetLogo, Mason, etc., where you can build these agent-based behaviors and so on. This is sounding something that we'll start connecting back to the course in later weeks. And so I don't want to dwell too much on that now, but if you have something specific in mind, I think that'd be a great topic for office hours over an email. So feel free to send that. So hopefully that answered that question. Okay. All right. So so kind of the motivations for at least where we're starting. Is heuristics. Now, does anybody in here, can you tell me, how many people are familiar with the word heuristic by a raise of hands? And if you're online, you can put something in the chat and say yes or no. Okay, so a handful of people are so to speak, look like they are, yeah, so and there's some comments here online. So I see some definitions here, I see people saying they have a general idea, yeah. So a heuristic is sort of a shortcut. And so we can think of, we have a number of problems. So if we have problems that we want to solve, a lot of times we can think of those problems like, so as an example, you might think of following distance in a car. Now, if you think about following distance in a car, choosing how to follow the car in front of you is a really complicated thing. Because if you are too far, then that often means that you're too slow and you never get to where you want to go. So you never reach destination. Now, if you're too close, you put yourself at risk. So if I wanted to, I could plot some sort of utility function of distance. And how do you even write this utility function? That's part of the problem here. And we know that as I get very, very close to the car in front of me, then my utility is going to be low because it puts me at high risk. If I, so maybe that's down here. If I get very far from the vehicle, I might be safe, but now I'm not going anywhere because I'm just constantly slowing down to put distance here. So maybe that's got low utility. And then there's probably some curve here where there is some optimal following distance. So this is the optimal following distance. And then the question is, you know, what is it? And how do we find it? Now, if we knew this function, this utility function, we'll call it f of x, and we can call this distance x and this utility f, then there are mathematical ways for us to solve for that exactly. Now, the thing is, you're probably not going to know that function. It's probably going to change from time to time to time. It might be very difficult to solve it, even if you knew what that is. And so what we do in our own lives is we build heuristics. So what are some heuristics that you might have heard for following distance? Yeah.
Like 3 car lengths or like double if it's raining or whatever.
Right, so that's a great one. So 3 car lengths might be one way you could say, I'm always going to follow 3 car lengths behind. Any other heuristics you might have heard for following behind cars? Some based on time, yeah.
Yeah, for 3 seconds before.
Right, so time-based heuristics, those are kind of cool too, because now at slow speeds, you follow closer, and at fast speeds, you get farther apart. So there's some elegance there in how they do that. Similarly, if you want to say, well, how do I convert from Fahrenheit to Celsius or Celsius to Fahrenheit? We know mathematically how to do that, but usually we do things like, well, instead of doing multiplying by 9/5 and adding 32, I'm just going to double and add 30. And that's usually pretty close. Similarly, these following heuristics, they might get us here in our utility function, here, and maybe depending on time of day, then it switches back and forth, but we're always pretty darn close. And so that's what a heuristic does. A heuristic is a simple rule that takes input from the environment and produces an output which is, under normal situations, pretty darn close to optimal. So there's simple rules that make us smart. That's what you can think about heuristics. If you think about it, an ANN, a neural network, is a heuristic itself. I'm not talking about how you train an ANN, but an ANN itself, as it's instantiated, or a neural network, takes inputs from the world, pipes them into a black box. It makes decisions, it does classifications, it does regressions or whatever, but we have no guarantee that it's going to give us the right answer. We have no guarantee that we're going to give it a picture and it's going to find all of the cats and all of the dogs and all of the balls. It may get some things wrong, but most of the time it does a pretty good job. So that's what we mean by a heuristic. So it's a tool that helps us make these normally good decisions. So if you think about a multi-objective or a multi-feature space where you've got things like color, distance, etc., and then you've got some optimization metric, then you might say a heuristic is, if I've got a bunch of choices, I always choose the one that's red, regardless of any other information that I have. And you could say under certain environments, maybe good choices, the environment is just naturally colored red for some good reason. So if I pick them, the work's already been done for me, and that's a good heuristic to use. But if I happen to move into another environment where whatever that process was that labeled the good things red wasn't there already, then choosing the red is not going to be a good option anymore. So heuristics aren't always good, but they're normally good under most normal environments. So the question is, how do we build heuristics? So we could come up with these heuristics ourselves, like how many seconds of following distance I have there, or we could have automation systems try to build heuristics for us. We could have neural networks be trained to do the best darn that they can. And that idea of how do I build heuristics brings us into the realm of meta heuristics. And a meta heuristic is a heuristic to build a heuristic. That's why it's a meta heuristic. And so the idea here behind this meta is we're saying, like, well, how do I choose? So my neural network, for example, I can feed it in a bunch of data, huge feature set. It's out, it knows the color of things, it knows the temperature of things, it knows all these different things out there. But I don't know what of those things will be a good cue for the right decision. I have a bunch of correct decisions that I have already recorded that people have made before, and I can load those into the neural network. And then that neural network can be trained to approximate all those prior decisions. And that training process is really a form of meta heuristic. So as an example here is training a neural network. And so there are a bunch of ways you can choose the weights in a neural network. And for those of you who aren't that familiar with neural networks, we'll talk about neural networks in great detail later. But what I'm just sort of getting at here is, in general, if I have inputs that are a bunch of different types of things, and I have an output, which is a function of those inputs, that output itself is going to be parameterized. And so that output may actually look like alpha times A plus beta times B plus gamma times C plus delta times D. And then the question is, what do these parameters need to be? And so we can build a search tool that searches over all of the parameters, effectively searching over all of the heuristics. And the search tool itself is going to be a heuristic to try to figure out what the best parameters are. So meta heuristics basically are automation systems that design good heuristics. And that's a big part of the first couple of weeks of this course, is talking about meta heuristics that are inspired by evolution, inspired by, in some point, genetics, but population genetics and just generally population methods in general. Yeah, question.
You're finding what the alpha, beta, gamma, and whatnot. So is it like this curve fitting problem essentially? You try to find the one that would give you these squares or something like that?
Well, that would be one meta heuristic you could think about using. I could say, what is the best linear fit in terms of squared error, something like that. And so that would be one approach to solve this problem. So another approach could be that I am not interested in, so what your approach would be sort of to minimize the squared error between this function and all of these data points that are around it. But you could come up with other metrics that you might want to minimize. So I might want to minimize the maximum distance between this curve and those points. I might want to, for some reason, I might have a constraint which prevents alpha, beta, gamma, and delta from having a sum greater than 1 or something like that. So then how do I deal with that? So, so there are a bunch of different approaches I could choose, and some might be mathematically justified and some may not be. Now, this particular problem seems like an easy one, but what if F is not, what if the mapping from the inputs to the outputs is not something that I can specify mathematically? What if F is a simulation, for example? Or what if F is a jet engine? What if these parameters are parameters of the jet engine? In order for me to evaluate how good F is, I actually have to run an experiment on a physical engine. So in that case, now choosing the heuristic is going to be much more complicated, because I won't, I may not have the math to guide me, and I may not even be able to run a bunch of samples in order to get there. And so that's kind of where we're heading for these heuristics. So the only other word that I want to then introduce here before I let you go is the next level in this, hyperheuristics. And so this is just providing a background for us to sort of then expand upon and then get more concrete next time. And what do you think hyperheuristics do? These are heuristics to build better metaheuristics. And so the basic idea here is a heuristic has parameters, which you can think of them as taking in inputs from the world and making decisions. A metaheuristic tries to choose the best parameters of a heuristic, but a metaheuristic itself can have parameters and how it searches over the heuristics parameter space. So then how do we make a better metaheuristic? Well, we can come up with hyperheuristics. Now, usually as we go from heuristic to meta heuristic to hyperheuristic. So this is heuristic, this is meta, and this is hyper. The hope is by the time we hit hyper, we have a low dimension of parameters. So basically the idea here is that, you know, if you're familiar with the neural networks, you might have, this is a neural network. This is maybe stochastic gradient descent, which has with its own parameters, like, so this might have regularization parameters, etc. And then, but those parameters of the stochastic descent can itself then be optimized. And there are optimizers that sit on top of the optimizer. So we have the final output, the optimizer, and the optimizer of the optimizer. And hopefully the optimizer of the optimizer, you only put in one parameter. You can say, you know, I tune one knob, and with one knob, it tunes 50 knobs, and those 50 knobs might tune 100 knobs. And so you then have much less to do because this ends up doing the search for you. And so we are looking at ways in which we can use nature to enhance the automation that goes through the search space here. And that's kind of where we're going to start off on Thursday. But I don't want to keep you guys any longer than that. You're already 2 minutes over. If you have any other questions or anything, feel free to come up after class. Otherwise, I'll see you on Thursday. I'm going to check online to see if there's any questions as well. If you don't have any questions online, then I also will see you Thursday. And I'll post this video a little later today. So thanks for your patience today, guys.
Thank you.
Thank you.
Just wanted to say, I saw you're in the Data Devils for Good
Oh, great. Yep.
Slack channel, so I'm in there too.
Great.
Neil. So if you ever want to work on something, you know, I don't know actually what if you're doing research these days, but yeah, feel free to shoot me a message or something.
Yeah, or likewise, if you find if there's something in this class that you think would be used for sort of a social good type project,
Yeah.
that would be a great mini project or final project, and feel free to bring it up and we can talk through if I can help with it.
Cool, absolutely.
Okay.
Thank you.
Nice to meet you, Neil.
Yeah. You too.
Hi.
I
You
was
said Quinn?
Quinn.
Okay.
I was just curious what the difference was, if any, between a heuristic and a lot of times in AI, I see the term policy thrown around a lot. I wasn't sure if there was a distinct difference or if they're just isomorphic to each other.
Excellent question. So I would say that that in some ways they're orthogonal because you can say, you know, you can say, how do you form your policy? We say, well, we use a heuristic to generate the policy. So we could say, well, what's this? Or you could say, how do you form this policy? Well, we actually solve for the optimal policy. So I would say that a policy is sort of the net outcome, and the heuristic or the mathematics or whatever are how you end up finding the policy. Does that make sense?
Yeah.
Okay.
Thank you so much.
Yep. And I'm gonna, if I don't have anything here, I'm gonna stop the recording here so I don't have to record everybody's. Okay.